400 kilometers away from you, there is a laboratory whose results no other lab can replicate. Those results do not fit with our day-to-day experience, as in this lab even time itself runs differently, slower than anywhere on Earth. That's because this lab is the International Space Station, and in this video, we'll see how even the most mundane of experiments have surprising results up there. But how is a laboratory even built in outer space? How does the human body survive there? And once the station's life is lived, how do you bring such a megastructure down from space safely? Join me today as we celebrate the ISS, a place where science and exploration transcend borders. The idea to have an orbiting habitable station in space has concretely been in our imaginations since 1868. The American author Everett Hale wrote about the Brick Moon, a space station made of bog-standard bricks. The US began taking the idea seriously in the 1950s, and then in 1984, Reagan gave the presidential order to build the ISS, which since its launch has been a marvel of scientific discovery. Over its decades of operation, the ISS has not only expanded our understanding of the universe, but also demonstrated the power of unity in the pursuit of knowledge. Which is an incredible achievement, given that its genesis owes much to a time when the Earth was a button press away from nuclear Armageddon. War has led to technological developments that seemed impossible in peacetime. Radar, jet engines, computers, nuclear weapons, and Marmite were all developed through a desperate war effort. A nation's fight to survive is perhaps one of the greatest motivators for technological advancement. And the Cold War, despite no shots being fired, was no different, because it pulled the trigger on the space race. But what about the times when there is no finish line? When there is no enemy to be conquered? Well, we wander. Incredible scientific discoveries are also often made when scientists are left to be curious, left to ask questions that sometimes seem to have no useful answer, and left to actually collaborate. That is how the idea for the International Space Station was born. The ISS was conceived after the ambitions of the USA's Freedom Space Station and the Soviet Union's Mir 2 were shelved, at a time when space spending was no longer justified by either government. Now, the space race was over. The ISS program today has the involvement of 13 other member states, including Canada, Japan, the UK, and other European countries. The ISS is a huge structure by any measure. Spanning 108 by 73 meters, it would just about fit inside a football pitch. It weighs a staggering 450 tons, and with an estimated cost to date of $150 billion, it's worth nearly 5 times its weight in gold. Clearly, it was never an option to launch all of this in one go, a move that would have been both impractical and extremely reckless. So the ISS was planned to have a modular structure, one to be assembled in space, piece by piece. Each module was designed and built by a member state before being launched into orbit on one of 3 vehicles: America's Space Shuttle System, or Russia's Soyuz, or Proton rockets. Remarkably, every launch carrying a component of the space station delivered successfully, numbering 40 to date. There have been delays and mishaps, of course, and some resupply launches have failed. But if a component made it to the launch pad, it's now part of the space station. The orbiting megastructure that we're familiar with today is comprised of 3 main sections. The backbone of the station is called the Integrated Truss Structure, ITS. It is unpressurized and uninhabitable, but it supports much of the functionality, storage, and equipment on the space station. The ISS was designed to bear 4 huge pairs of double-sided solar arrays, capturing light from the sun and rays reflected from the Earth, which can generate 248 kilowatts at peak. But the ISS can only generate electricity for 45 minutes per orbit. So, the station requires batteries to power the systems while the sun is eclipsed by the Earth. Much of the power usage on board is ultimately transformed into heat. So, the station needs large radiators capable of discharging 70 kilowatts of heat into space in order to safely regulate the temperature on board for its inhabitants. Below the ISS, the space station is divided into 2 pressurized and habitable halves: the Russian orbital segment and the United States orbital segment. If you enjoyed this video, don't forget to like and subscribe to support our channel. So how was all this built? Where would you start? Let's watch several key stages of construction to understand how the whole can be built. The first module put into orbit was the Russian Zarya module in November 1998. This module featured 4 docking ports ready to accept the future modules and solar panels to provide the station's first power source. The next mission launched later that year from the John F. Kennedy Space Center in December, carrying the Unity module. The docking of Unity to Zarya would mark the beginning of a new global space age. Inside the space shuttle, the Unity module was equipped with 2 pressurized mating adapters, PMAS, that interfaced the American ports to the Russian port and to the space shuttle's ports. The space shuttle was fitted with a robotic arm called the Canadarm, which could attach to the 12-ton Unity module and position it above the space shuttle's docking port. This movement had to be done extremely slowly. Once aligned, the shuttle's thrusters were fired to engage the ports. When Zarya was reached, the Canadarm was again used to reach out and grab the Russian module and guide it towards the PMA on the Unity module. When it was in place, the thrusters were carefully engaged to make the connection. After a few checks, the joined space station was released, after 2 weeks of maneuvers. With only these 2 modules, the station was uninhabitable. But that changed in July in 2000 with the launch of the Zvezda module from Russia, bringing life support and living quarters for 2 astronauts. Later that year, the Z1 truss module was connected, ready to join the habitable orbital segments to the ISS. And that November, Russia launched 2 cosmonauts and an astronaut, Yuri Gidzenko, Sergei Krikalev, and Bill Shepard, to the space station to become its first inhabitants. Their docking marked the last time that the space station would be uninhabited, and a crew has been on board every day since. For the first 4 months, until the first laboratory module, named Destiny, was attached to the space station, the astronauts were methodically commissioning the station's key systems and assisting with the delivery of further modules. In April 2001, an incredible tool was delivered by the space shuttle, a device that could maneuver objects in space without the need to complete a spacewalk, called the Canadarm 2. It was the successor to the robotic arm aboard the Space Shuttle Endeavour. It could be attached by either end at specific power data grapple fixtures across the station. This means that the arm had the incredible ability to walk across the station to different locations to assist wherever there was a PDGF. A future Endeavour mission in 2022 extended the utility of the Canadarm 2 by delivering the Dextre, a telemanipulator, essentially giving the Canadarm 2 a hand. Over the next 10 years, modules were continually added, including 5 more laboratory modules from Russia, Japan, Europe, and the US. Research aboard these laboratories is truly multidisciplinary, and the questions studied can span fields including astrobiology, astronomy, physics, chemistry, space weather, and space medicine. By the end of 2009, the last of the main solar arrays had been installed, meaning that the ISS finally appeared like it does today. not all the planned modules made it into space. The Columbia disaster in 2003 led to the cancellation of some projects, including the artificial gravity module, a module that used centrifugal force to simulate anywhere from 0.01 G to 2 G for use in experiments. Artificial gravity has been a mainstay of sci-fi, and it would have been extraordinary to see humanity test its own system on the ISS. Not least because the astronauts and cosmonauts would have appreciated it, too. The absence of gravity on the station is a huge complication for day-to-day life. Almost nothing behaves as you would expect, ranging from the mundane to the deadly. Even the simple act of drinking a coffee made by the station's barista, the IS espresso, could be risky when you're surrounded by sensitive scientific equipment, zero gravity, and 100 laptop keyboards. A significant part of the station's research program has been on understanding the behavior of objects, fluids, and people in a zero-G environment. And if Trump's recently announced manned mission to Mars is to be successful, a trip that would take up to 10 months each way, it will stand upon the research from the ISS. Studies on the past crews of the station have shown how in the chronic absence of gravity, the human body will ruthlessly atrophy any organ or structure that is surplus to its requirements. Organs are expensive to run. The musculoskeletal system in particular will degrade, bones weaken, and the heart shrinks. Careful exercise regimens must be planned in order for the crew to maintain bone density and heart function and for their physical health. The ISS is equipped with a custom gym so the crew can maintain some of their fitness. But despite all that equipment, it cannot fully simulate the coordinated strength and balance required to walk on Earth. And the astronauts effectively have to relearn how to walk on their return. The lack of gravity affects other organisms too. In space, even microbes behave differently. Aboard the ISS, zero-G has been found to alter the gene expression of certain salmonella pathogens that just so happens to have the effect of increasing their virulence, making them deadlier. Well, I guess it could have gone either way. More immediate problems also present themselves in zero-G. Fire is of course dangerous in most situations. But on Earth, we at least have an intuition for how it moves and behaves. In space, fire can expand in any direction because without gravity, there is no convection. And so the less dense hot air no longer rises. Flames in space can sit and persist, or even be invisible for lengths of time, because a low burn rate can be sustained by diffusion. Smash that like button and hit subscribe so you won't miss what's coming next. Because without convection, even attempting to boil a kettle is going to land you in a pot of hot water. The Nucleate Pool Boiling Experiment, NPBX, was designed to study this exact problem. Because without convection, how do you achieve efficient heat transfer in space? A kettle in space would be hampered by the formation of a large bubble at the heated base. Not that you would particularly want a hot cup of tea because, in this convectionless environment, the body cools less effectively. So, the atmosphere in the habitable areas needs to be well circulated. Other fluids need to be actively moved around in space by fans and propellers too. And, as is the theme, even these behave differently in zero-G. Fast-moving propellers can cause cavitation in a fluid, where a cavity is ripped open in the fluid and then explosively collapsed by the surrounding pressure. That collapse releases shock waves that carry large amounts of energy and can cause significant damage. Meaning, that propagation needs to be understood so that our equipment can go the distance on any space mission. Incredibly, research into cavitation in microgravity on Earth provided insight into the most explosive acts in our universe, supernovae. a previously unexplained supernova form, has been linked to the collapse of bubbles in a fluid in 0G, under a process called eccentric core collapse. These experiments so far are all critical for the success of any future long-duration space travel. But the ISS runs powerful physics experiments too. In addition to the 6 pressurized laboratories, the ITS carries an experiment called the Alpha Magnetic Spectrometer, AMS, one that NASA considers as important as Hubble, and one that requires so much power and so much bandwidth that almost no other vehicle in space could run it. But what does it do? It's a detector, the business end of a particle accelerator. Space has cosmic voids with hidden objects that can generate particles with energies equivalent to a pitched baseball. Think about that. 240 exa-electron volts. Millions of times more powerful than what our biggest accelerators can produce. Its stated aim is to research dark matter, specifically to search for evidence of a hypothetical particle predicted by supersymmetry called a neutralino. Moving on from the hottest particles in the universe to the coldest. NASA's Cold Atom Lab was designed to explore the quantum properties of matter and can reach temperatures of 1/10,000,000,000th of a Kelvin. It was the first to produce the 5th state of matter, a Bose-Einstein condensate, in 0G. On Earth, these condensates eventually collapse due to gravity, but in space, they float and persist. The crew has even been able to synthesize atomic bubbles on board the ISS, a form of macroscopic quantum behavior. Long-lived BECs in orbit is a significant step, and they have uses. Atom interferometers can be made that can be used to measure gravitational waves in a way that complements LIGO's capability. Atom interferometry using BECs would be able to capture the middle band frequencies of gravitational waves that LIGO cannot detect, allowing us to detect different objects and probe quantum gravity more precisely. The AMS isn't the only external experiment on the ISS. The Japanese laboratory module, called Kibo, has a facility known as the Terrace. In the vacuum of space, Kibo has been crucial in gathering climate data with sensors to perform atmospheric gas monitoring, ecosystem thermal imaging, and experiments with laser communications. It also featured a hyperspectral camera to take images of the ocean around complex coastal areas. Typical cameras record in 3 bands, R, G, and B. But a hyperspectral camera records wavelength information across the entire visible spectrum, which along with the other data recorded provides a rich data set to understand the effects of climate change. Not only is the space station helping us to soar from the Earth, it is, perhaps more importantly, helping us to continue to walk upon it. The International Space Station is more than a scientific laboratory, though. It is a symbol of what humanity can achieve when we cooperate and reach for the stars. As we look to the future, the ISS reminds us that the boundaries of exploration are limited only by our imagination and our willingness to work together. In the 2030s, the ISS will complete its final mission. In a carefully orchestrated process, the station will be deorbited, with its remains safely scattering across the Pacific Ocean. While its physical presence will be gone, the knowledge and inspiration it has provided will continue to shape the future of space exploration. The end of the ISS will mark the beginning of a new era in space exploration. Private companies like SpaceX and Blue Origin are poised to take on greater roles, while international partners have already begun planning next-generation space stations like Orbital Reef and Lunar Gateway. The lessons learned from the ISS will guide these efforts, ensuring that its legacy lives on. The International Space Station is an incredibly ambitious project that has spanned decades, and in this video, we've only scratched the surface of its contributions to science. If there's an ISS topic you'd like us to explore in more depth, let us know in the comments below. Thank you so much for watching until the end. If you found this content valuable, don't forget to give us a like to support the team. And make sure to subscribe and hit the notification bell so you won't miss our upcoming videos. See you next time.